Hello everyone. In this video, we will see the electrophilic addition reactions of alkene and alkyne. So the points of discussions are, first point is the why alkene and alkyne shows electrophilic addition reaction. Here we will elaborate the reason behind the addition reaction of alkene and alkyne. In addition, we will see the general reaction of electrophilic addition and its mechanism. And the last point in this video is the example of addition reactions, that is addition of HX, hydrogen halide, addition of hydrogen, addition of halogen, HOX, water, boron and ozonolysis. So let's begin with the first point, why alkene and alkyne shows addition reaction. For that purpose, we have to go through the structural aspects of alkene as well as alkyne. Here on the left hand side, ethene is written and its structural aspects, how it is undergoing the hybridization, and on the right hand side, acetylene is taken. So let's start from the ethene molecule. It is also called as the ethylene. The formula is CH2 double bond CH2. Here the carbon which are present in this ethylene molecule, they are in a sp2 hybridized state. So sp2 hybridization is there, and in case of sp2 hybridization we get 3 sp2 hybrid orbitals and one unhybridized p orbital. Now these sp2 hybrid orbitals, they are used for the formation of a sigma bond, whereas a unhybridized p orbital which remains perpendicular to the plane of this carbon, then it is used for the formation of a pi bond. Now here you can find the structure of ethylene. Here there is a presence of one pi bond and one sigma bond. Now out of the 3 sp2 hybrid orbital of this carbon, 2 sp2 hybrid orbitals, that is these two ones, these are the 2 sp2 hybrid orbitals, they are used for the formation of sigma bond with the hydrogen. This is the orbital of hydrogen, so there is a sigma bond formation, and one sp2 hybrid orbital is used to form a carbon single bond, a carbon, that is sigma bond between the two carbon. So here it is one sp2 hybrid orbital is used. Similarly, in this carbon, it uses 2 sp2 hybrid orbital to form a bond with the hydrogen, and one is utilized in the carbon-carbon sigma bond formation. Now, this p orbital which are unhybridized one, they remains perpendicular to this sp2 hybrid orbitals, and they undergoes a sidewise overlap with each other. So these p orbitals which are present on the two carbon, they overlap sidewisely and they forms a pi bond. Now we know that sigma bonds and a pi bond, out of which the pi bonds, they are a weak one and they are unstable one. These pi bonds, they are loosely held by the carbon nuclei, therefore they are available for the bonding purpose. And the alkene possesses a pi bond which are loosely held, therefore this side, it is the reactive side in case of alkene. Any alkene, ethylene, propene or butene you may take, the pi bond is the reactive side in the alkene molecule, and it going to react with the reagent which are electron deficient one. So here this pi bond they undergo a reaction with the electron deficient basis, and that electron deficient basis is called as a electrophile. So the alkene molecule undergo a reaction with the electrophile, and when it undergoes the reaction, it will break a pi bond and they forms a new sigma bonds. How many sigma bonds? Two sigma bonds. So from instability, they goes towards the stability by breaking the pi bonds and forming a new sigma bonds. This is called as a electrophilic addition reaction of the alkene. Therefore, alkene possesses a pi electron, which is the reactive side, and it will go to react with the electrophile. That's why it shows the electrophilic addition reaction. Now you can see here the p orbitals, sigma bonds, and how they are oriented in case of ethene molecule. Similarly, in case of acetylene, there is a carbon triple bond carbon, out of which one is the sigma bond and two are pi bonds. Now in this molecule, the carbon which are present, they are in a sp hybridized state. That is, there is a two sp hybrid orbitals and a two unhybridized p orbital present on this carbon. Let us consider first carbon. Here you can find this is the sp hybrid orbital which forms the sigma bond with the s orbital of the hydrogen. Similarly, on this carbon, this sp hybrid orbital forms the sigma bond with the s orbital of the hydrogen, and the remaining one sp orbital on the each carbon, they undergoes a sigma bond formation with each other. This is the sp hybrid orbital of the carbons. So two sp hybrid orbitals, they are used for the sigma bond formation. Now the two unhybridized p orbitals which are present on this carbon, they are drawn like this. This is the first p orbital and this is the second p orbitals. They are perpendicular to each other as well as the plane of this carbon single bond carbon. Now they overlap sidewise with the another p orbitals which are present on the another carbon. So this will overlap with the p orbital which is present on this carbon, and this it will overlap with this. So there is a formation of two pi bonds. In this way, in alkyne also there is a pi electron or a pi bond, and it is the reactive site in the alkyne. It will undergo a reaction with the electron deficient basis, that is electrophile. That's why alkyne also shows electrophilic addition reaction with the electrophile. Now, when we compare the electrophilic addition reactivity in case of alkene and alkyne, it is found that alkenes are more reactive than alkyne. You may confused here. Alkyne possesses two double bonds, that is two pi bonds. Alkene possesses only one pi bond. So as per the discussion, when pi bonds are more reactivity should alkyne possesses. But this is not the case. Alkenes are more reactive in an electrophilic addition reaction than alkyne. It is due to the, in case of alkyne, the pi electrons, they are strongly held by the carbon nuclei. That's why they are not easily available for the bonding purpose. Whereas in case of alkene, the pi electrons are loosely held. by the carbon nuclei. That's why they are used or easily available for the bonding purpose. This is the difference between alkene and alkyne. But we should keep in mind alkene and alkyne always shows a addition reaction due to the presence of pi electron in their structure, which is the reactive site for addition reaction. Now we will see the general reaction and the mechanism of electrophilic addition reaction, how the reaction occurs. In the general reaction, we have taken the alkene molecule, carbon double bond carbon, whatever may be the substituent which are present here and here. It reacts with the addendum and it gives the addition product. Now, what is the addendum? Addendum, it is the electrophilic reagent which is going to add across the carbon double bond carbon. That's why it is called as a addendum. It means which is going to add. Now this XY, out of which Y is more electronegative. More electronegative. Now, in the mechanism, what happens? This is the alkene molecule. Here, there is a carbon, single bond carbon, that is the sigma bond. And these are the pi bonds. They are formed by the sidewise overlap of the p orbital present on the each carbon. So, here it is nothing but the pi bond, and we know that the pi bond, they are reactive side in case of alkene as well as alkyne. Now what happens when this addendum or electrophilic reagent, it came contact with the alkene molecule, then due to the presence of pi electron or a pi bond, this molecule, that is electrophilic reagent, it undergoes a polarization, and here we get a pi complex due to the polarization. So X is more electropositive, Y is more electronegative. That's why Y carries a negative charge, whereas X carries a positive charge. And this polarization occurs due to the close contact with the pi electron or a pi bond. And here we get a pi complex. Here it is a pi complex. Now, in the next step, this pi complex, it will collapse to form a carbocation. So this X, which is more electropositive, it will going to attach on this carbon or on this carbon. When it going to attach with this carbon possesses a positive charge because the pi electrons which are present here, they are utilized in the formation of carbon X bond. So the electron from this carbon, they are shifted to form the bond, and it is a positively charged. Here we get a carbocation. Now, in the next step, the Y minus, which is removed in the formation of this carbon X, this Y minus, it will attack on the carbocation to form a addition product. This is the simple mechanism. It is observed in all cases of addition reaction, but there is the one condition or one situation where a different mechanism is observed. Suppose we have taken X and Y. Here X is also halogen and Y is also halogen. Now, in this case, halogen possesses a lone pair of electron. That's why in such a molecule or in such a electrophilic reagent, if they possesses a lone pair, a different mechanism is observed. In this case, what happens when this Br2 molecule or any halogen, that is X2, when it came in contact with the alkene, then we get a halonium ion as a intermediate. The structure of halonium ion, or in case of this bromonium ion, I will draw here. Here we get this type of structure where the bromine is forming a cyclopropane ring with the two carbon, and it possesses a delta positive charge. It is called as a bromonium ion. So in case of Br2 molecule or X2 molecule, we get a bromonium ion or a halonium ion rather than a carbocation. And this bromonium ion in the next step reacts with the another Br, and it will form a dibromo compound where the addition of bromine take place from opposite side. That is, one Br add from the upper side, whereas one Br add from the lower side. It is called as the anti-addition. It is possible only when if the electrophilic reagent possesses a lone pair, generally in case of addition of halogen. So details about it we will see in the addition of halogen across alkene. So in this way, the mechanism occurs in case of electrophilic addition reaction. In all cases, most of the cases, I will say, there is a formation of carbocation, and in case of halogen, there is a formation of halonium ion. Now we will see the general examples of electrophilic addition reaction. So from this diagram, you can see the different examples of addition across uh, carbon double bond carbon. It is the carbon double bond carbon. It will undergo addition of H2. It is called as a hydrogenation. In presence of metal catalyst, it will form a alkane. Two hydrogen molecules, they are add across the double bond. Where it also shows the halogenation in presence of inert solvent, that is a protic solvent. X2, that is halogen. It will shows a dihalide formation. But when this halogen is added in presence of the water molecule, one halogen is going to add and another is the OH. It is called as a halohydrate. So there is a difference between these two addition reaction. When inert solvent is added, then we get the addition of two halogen across double bond. When water is used, then there is the addition of halogen as well as the OH group. It is called as a halohydrin or addition of HOX. The next is the addition of halogen as well as a hydrogen. It is called as a hydrohalogenation. It gives the formation of alkyl halide H and X. Here you can see the addition of water molecule. It will give alcohol. Then the next is the addition of boron. It is called as a hydroboration oxidation process. In the first step, boron is added to give carbon single bond BH2. Now this boron, it is oxidized to form the alcohol. So in case of water molecule, we get alcohol, or in case of hydroboration and oxidation, we get alcohol. But the difference between these two alcohols are this alcohol is obtained according to the anti-Markovnikov addition. Anti-Markovnikov addition, whereas this alcohol is obtained by a Markovnikov rule. The next reaction is the hydroxylation process, where alkene is treated with the potassium permanganate. Here we get the addition of two OH group across the double bond, and there is a formation of diol. And the last one is the ozonolysis process. In the first step, there is an electrophilic addition of O3 molecule to form a ozonide. It will oxidize in presence of zinc and water, or we can take here a hydrogen peroxide, so that here we get a carbonyl compound. So all this reaction contains a electrophilic addition of a electrophilic reagent that is called as a addendum across the carbon double bond carbon. And we will discuss all this reaction in the upcoming videos, and there are details with the examples. So this is all about the electrophilic addition, that is general introduction, why alkene and alkyne shows electrophilic addition reaction, general reaction mechanism, and the examples of addition across carbon double bond carbon. So in the next video we will see the most important reaction in this point or in this topic is hydrohalogenation reaction. So with this we will stop here, and thank you for listening me once again.